Okay, so this is the second session. It's very similar to the first one. The first one we just testing, so there's not a lot of audience. And second one we have much bigger audience. So first of all, we'll introduce a little bit about who is ZoomAFM.com. Sorry, I did not update. I did not know there's so many of us is joining in. We are a support platform, and we have we all of us the support engineers and scientists. We used to work for Agilent Technologies. Here I have myself, Steve Raba, who's in the audience, and XQ, who's the senior manager. And today we have two more joining in, Louis Vachenko from France and Gerald Carter. Gerald Carter, are you in Germany? Anyways. And we want to come here to provide the support so we can keep your instrument run for 10 more years. We try to do this by support the molecular imaging, Agilent technology, and KeySight technology AFM users, some of the selected models, not all of them. We will provide lecture and training and repair and maintenance. So if you have questions, problems, you can come to this ZoomAFM.com, talk to the people who has many years of experience working on your instrument, and welcome to email or just go to ZoomAFM.com. There's links there, and then so on and so forth. Okay, so this is the entry point, which is the ZoomAFM.com. This is a link that you can click there. If I happen to be near my computer, you can give me a call, say, I have a problem. Do you have time? You can go to this link and then you can talk to me and then use your phone to point to your instrument and I can answer your questions. This makes it very easy. And NanoKit technology, and then is basically my business. And then I did built a lot of liquid cells modifications for AFM application. And Honkyo is the service business of Steve Raba, who is also in the audience. And then he is the master when something is not working. Okay, I'm the master when everything's working. I'm very good. So this is lesson 2 now. It's almost a repeat of lesson 1. It's introduction to atomic force microscope feedback. But from the feedback of the first session, and people telling me I'm still talk a little bit too fast and cover too much materials and not enough details that is covered. So that's why we have the second one. I'm going to slow down and then cover things in more details with a lot of simulations. And there's a lot of fun stuff that we're going to do here today. Okay, so this is the contact mode AFM cantilever. It's a beam of silicon nitride, and there's a little tip, pyramid there that touch the sample. And as the tip touch the sample, the force between the tip and sample will cause the cantilever to bend up or bend down, depends on the force is repulsive or attractive. And then we use a laser to shine at the back of the cantilever, and the laser will bounce back, and we use a detector, PSPD detector, to detect the bending or the deflection of the cantilever. Simple, we know that. So here is some pictures of some of the tips, and some of the tips are very sharp. And we all know that the quality of the tip impacts the image, and why the quality of tip impacts image. Here at right-hand side, there is little things here was covered by here. Anyways, I'm going to turn on this simulation, which show you the quality of the tip that actually impact your image quality. Here is the simulation. Okay, good. It's very nicely made, and thanks to Joseph Griffin years ago, he allows me to download his simulation when I was attending his Lehigh microscope school. And then he said, oh, okay, go ahead and download it, and you can play with it to see how the tip shape impacts your image. So here I have this, suppose my tip is very sharp. Okay, The tip is basically AFM tip has a complicated shape. You sometimes we can simplify it by think it is a, let's say, a needle or a pyramid or a palabra, right? It's all of them are just a simulation. And then this simplify our thinking by say I have this palabra that is very narrow. Okay, so sample and it's have this rough surface, and then if you scan the tip over your sample, as you can see, if you maintain the tip and sample at a constant contact, in this case contact mode, the movement of the tip is a profile. This profile has a Z direction and an X direction. There's no Y direction, just X and Z. And this profile represents the topography shape of the sample. Okay, and then this is how AFM works. It's basically not a picture, but a series of these profiles. And if you move the profile from forward and cover the surface line by line, we call it scan. And then this profile represents the shape of your sample. Now, what if my tip is not very sharp, right? What if this is, let's say, a pyramid, but the pyramid is not sharp, so it's got a little blunt surface. Okay, so as you can see, you scan over the surface, and when you scan over the surface, the profile no longer hug the surface of your sample. The profile basically is the sample plus the shape of the tip. Okay, so we call it convolution, right? So that's why you need to have a sharp tip, a blunt tip. Your image will appear to have a lot of shapes repeating itself, because the image, the profile is really the shape of the sample plus the shape of the tip. So you have a dull tip. The tip itself is not a close to a point. Then your image will be dull. We have a big chunks of data sometimes looks very interesting. Later, I'll show you one of the interesting data. I was actually giving my first presentation this way last Sunday night, which is Monday morning in China. And students say, I discovered something that is very interesting. There's a lot of baby face on it. And there are baby face everywhere, and all the babies are point their head at the same direction. And immediately I know that's tip effect. That's because your tip is not sharp anymore. Okay, so if you think the tip is palabra, same thing. That the image is a convolution. Okay, let's move forward. So next we'll look at the feedback. So again, I'm going to just use the contact mode as a examples to discuss, because tapping mode, things gets a little complicated. I prefer you think the way in a simple way. So this is a force curve. The force curve is a force measurement between the cantilever and the sample when you move the cantilever up and down into and out of the sample. Okay, so here the flat line, the force curve has two lines. One is the line here, this guy. I try to put a different color, but the same color to me. Anyways, two lines. It's approach curve and withdrawal curve. When tip and samples are far away from each other, the force is 0. And then as the tip getting very close to the sample, the van der Waals force between the tip and sample pull the tip into the sample, and therefore you have this little snap, which tip is sucked into the sample. And as you push the tip further, the force will increase. And then if you pull the tip away from the sample, the force will decrease and snap back. That's the basic force curve. The early atomic force microscope, before the invention of tapping mode, it's a contact mode. Basically, it works what works the best in a repulsive region. In other words, I'm going to push the tip into the sample, and the tip and sample is going to look like this here. Let me see, there's a chat in the room. Oh, that's someone say hello to everybody. Anyways, so if I put a set point here and then we'll compare the measured deflection signal. Here is actually what you measured is not actually force, it is a deflection. It is the movement of laser spot that's bounced from the top part of the cantilever. Okay, so I'll put a set point here and I put a measurement, put a calculation of between the measured deflection and the set point. We call error, the difference, and use that feedback. We can use this feedback to image the topography of your sample. All right, let's talk a little bit about the scanner. These are two different kind of scanners of early designs, and then they're made of tubes, and then they're very simple, relatively simple to build. Okay. So this scanner has two sections, and then top section and bottom section. The bottom section will apply voltage to the scanner and then cause the scanner has some kind of internal stress. This internal stress causes the scanner to bend left and right. And we can use this bending of left to right to scan the scanner over a certain distance. And then the top portion of the scanner is we apply voltage universally. This way will cause the tube to expand and contract. And this will move the sample against the tip on the Z. This gives us a 3-dimension freedom to scan the sample over the surface, and then also to move the sample up and down. Okay, this is a sample scan instrument, and this is a tip scan instrument. A tip scan instrument, you just reverse that. Sample is not moving. The tip is fixed at the end of this tube, and then the top portion will move X, Y, and the bottom portion moving in Z, and the scanner will move up and down, and so on and so forth. So almost all the adjuvant AFM later Keysight or molecular imaging early were of tip scan design. And the design is actually more complicated than that, but we are not covering these design details today. So in order to make this whole work, you have to aim your laser to a particular portion of the tip, and then use a detector to detect the deflection of this cantilever. So this one shows the basics mathematics of the feedback. And then here, I want you to take a look at this one on the left lower corner. And suppose you have a sample that has up and downs here. Suppose you have sample has an up and down. Okay. So as the scanner moves forward, the tip is going to hit something with an upper slope. For example, there's this little bump, and tip is actually climbing up the slope. When the tip is climbing up the slope, as you can see, when you climb up, you need a lot of effort, right? So because basically for the tip, it is experiencing increase of the deflection force. So the deflection signal, I call this deflection error. The error means the deflection signal minus the set point. It's the error. Basically deflection signal, and then you move the set point, and then the difference here is error. This error, deflection error signal started to show a maximum positive number. And then we look at this PID feedback here, Z, which is the Z voltage that we apply to the scanner, Z equal to P, which is a proportional gain, times the Z error, and plus the integral gain times the integration of the Z error with time. And then we also do the acceleration, the dz dt. This is the feedback, the normal, the PID feedback. How does it work? But in our instrument, I think the integral gain is most sensitive. So we mostly adjust the integral gain, the I gain. So if you look at the instrument, you have P gain, I gain. P, you can just fix at a certain value, and then you adjust I gain. So what happens to I gain? I gain is that when the deflection signal is increasing, means your force is increasing. And then this formula tells you that because my force is increasing, I need to decrease the force by lift the tip up. And then, so I will put this error signal, integrate with time, and we will add the signal into the Z. Add signal right here. Okay. So as you can see, as my tip is climbing up the hill, the Z signal start to increase. So I'm going to apply this to Z, this DZ, which is the Z voltage increase. As it increases, it will lift the tip. Okay. Right. Let's look at the other situation. Then tip is climbing down the slope. Here it looks like tip is already at the bottom of it. It's climbing down the slope. When the tip is climbing down the slope or going down the slope, right? You go down slope, your force decreases. And you're moving down. So you can look at here. I need to move this a little bit to left. So deflection arrow is turned into negative from this portion down slope. When deflection arrow is negative, as if you look at this integration, this Z arrow is negative. And as you integrate with time, it does not immediately turn your Z high voltage negative. It just started to decrease the voltage. Okay, so as the tip is climbing down the hill, the feedback loop, the integral feedback loop, integration with time, is going to decrease your Z voltage. In other words, it's going to try to lower your tip. As you lower your tip, it will allow you to maintain the deflection arrow signal not going too negative. In other words, maintain a constant force. So as you can see, if you move up, the tip, the Z will increase, and then if you move it down, tip will decrease, right? When you do that kind of operation, and the high voltage to the Z, if you compare the one on the top, someone has a little feedback. You probably should mute yourself. Yeah, so as you move forward, you can see the actual topography and the feedback output, they look the same. In other words, when I try to use a feedback to maintain the deflection signal not far away from the set point, essentially maintain the Z arrow to a minimum. When I do that, the output voltage to your Z piezo mimics the surface topography. And when we output this channel into a data collection, that is the essential basics of how the feedback works. That's how it works. Okay, so again, we have a little game to play. Let me get out of this, and I will show you this simulations. Again, thanks to Joseph Griffin from Lehigh Microscope School in 2003. Okay, so let me stop the scan. Here I have a scanner moving in XY, and then if I increase my height, as you can see, when I increase height, deflection started to increase. It's detecting my sample. Okay, good. So now if I scan, let me go scan it. Increase height a little bit more. Okay, great. So now my tip is moving up and down because the surface is moving up and down. Okay, it's perfectly okay to output this signal, this deflection signal, into a image and maintain your feedback at minimum. It's perfectly okay, and then you can get a topography image or something look like a topography image. However, when you use this signal, depends on how fast you scan. This signal actually, you cannot calibrate it. It's very difficult to calibrate because, today I have this laser, and tomorrow my cantilever is slightly oxidized, so the signal is a little bit less, and therefore this output signal will be less. So instead of using the deflection as your topography output, what we do here, let me stop the scan. So we're going to apply another thing. It's called the feedback. So here is the feedback, and if I lower the sample a little bit, oh, great. You see that this blue things show up. What is this blue thing? This blue thing is your Z feedback. Okay, here's how to work. When I scan myself forward, okay, what happened? The force increases. And here's a Z arrow, the deflection minus this set point. Here's a set point. Okay, Deflection minus set point is a positive. When I have positive, I will try to, in adjuvant AFM, I try to lift the tip. This is a sample scan AFM. It just reverse the polarity. I will lower down the scanner. So if I apply a feedback, it just lower down the scanner in order for the signal to maintain at the set point. So now, what if I scan forward and I hit something that's lower? Okay, the sample's not high enough. Okay, so we hit some area that is a little bit lower. Oops, that's difficult. Maybe lower the sample. Okay, it's lower. It is a little bit lower. Scan it. Okay, lower. So when there's a lower, I have a negative Z arrow. When there's negative Z arrow integrate into the scanner, it's actually feedback and try to increase the force by close the distance. So now if I continue to do the feedback, okay, just continue to do the feedback like this. Adjust sample height. What happened? This is what happened is that the force, the Z arrow or the force, measure the force compared to the set point is maintained at a constant or close to constant, while your scanner is moving up and down on Z. So as you can see, the movement of the scanner actually mimics the topography of your sample. Okay, this is how this feedback works. And in the next couple of classes, I'm going to use this model a lot. And if you want to play with it, send me an email. I can send this one to you. And because I got the permission from Dr. Griffin, and he said, oh, yeah, go and share with other people as long as you keep my name here, not to delete it. So, yes, you can email me. I can send you this program. You can use it to judge what's happening to your instrument. Okay, this is how this topography works. Let me close this down. All right, back to the feedback. So the tip is scanned over the sample. It forms lots of lines, line by lines. And then the computer will add the color to these lines. And then we'll, in this case, use the height as a color. And then when we have spot that is higher, give you a brighter color. The lowest spot give you dark color. And then it render it into a three-dimensional image. And that's where how the feedback turn into AFM image. Now, let's look back to the early, we talked about the tip convolutions, and we want to have a sharp tip. And a sharp tip has two different meanings. One is the tip has a high aspect ratio, means it's taller than its width. And there's another measure of the tip sharpness, which is the radius of the tip. And what is radius? Is we can imagine the end of the tip is actually a ball, and that's the radius of the ball. And then the image itself is actually the convolution between the tip and sample. It's the shape of the sample plus the shape of the tip. And then when we have used a tip with a very small radius, the image is more true to the sample. And if we have the tip that is very tall and very slim or high aspect ratio, it also gives you a more close the shape between the topography and actual image. So I will finish my today's presentation. I don't want to talk too much because I want to leave time for everybody to communicate. This is an image a student sent to me this past Sunday. And she said, I discovered a lot of little baby face and what's going on. And then let's take a look at these little babies. And these little babies have heads and then have little arms, says hello, and body. Okay, and they look the same to each other and they are the same orientation. That's because, as I earlier said, the image of the AFM topography is the shape of your sample, which are those particles, plus the shape of your tip, which are these little babies. So this is actually the shape of your tip. And this is, if you flip your tip around, if you look at it, it should look like this. That's because of the tip is actually pick up something and it's getting dirty. And then you see all these repetitions. That's because when you use tip to image the sample is also imaging your tip. I will thank you for your attention, and again, come to our website and check out anything new. Next week, we're going to talk about how tapping mode works, and we'll talk about the oscillations and phase imagings and so on and so forth. And then if we have time, we'll continue to talk about how to improve the resolution of the tapping mode. Well, thank you for your time. I'm going to read the chat. If you have questions, please unmute yourself and then start chat with each other. And this is the purpose. We to chat each other. I don't want to talk for an hour. Go ahead.
Hello,
Yes, go ahead.
sir. If I want to understand, learn the analysis of AFM data, is there any r- source of learning that how we can process my data through gradient software?
Yes, I have 3
Any
hours of
tutorial?
presentation that talk about data processing. And
Okay.
if you like or other people agree, I could move this earlier. I can talk about it. Again, keep coming back. And also, we're going to post these videos online and we'll cover those. And I have a question for you. And what sort of software you're using to process your data?
Actually, I have taken data till now, but I have not processed yet. But I want to learn it through some kind of software. So I want to know from you that how I can proceed. If any kind of tutorial I can get to process my data.
Yes, we can do this by, you can try to find me on my zoomafm.com, also email me. And actually, I can type my email here, so you can email me. What I want you to do, okay, I'm going to type on in the chat and my email address. And so what I want you to do is to do a screen capture of your instrument software, the computer. Okay, do a screen capture so I can have an idea what software you're having right now.
Okay, sir.
So I can uh, tell you how to do that. If you happen to use the basically Agilent Pico image, and I have the latest version of that dongle, so I can process the image, and then I could spend one of these sessions and just process right in front of you. You can see me how doing it. There are three and a half hour lecture particular about data processing. It is a very complicated and then very informative to spend a lot of time to process the data. Typically, I spend 2 hours of data processing for 1 hour of imaging. I would just sit there and then play with back and forth. And there's many things you can do with it. Now, I understand a lot of the instrument that you're using are not very new anymore, and then some of your computer is no longer working, and then uh, some groups replace computers. So the the Pico image may no longer work, and if you want to purchase the Pico image, I'm gonna try to link you with the company who makes that software. Again, that's expensive, and then if you are try to do something that's low cost, I would recommend Gradient, and then I will spend time on Gradient and try to put together a presentation on how to use Gradients. Yes, do email me and then show me what is it do you have. If you have Pico image, that's great because I have lots of experience in play with the Pico image.
Okay, I have taken my data in the area of 2 by 2 micrometers.
2 by 2 micrometers. And what is your sample?
My sample are the of FeCOB thin films of 50 nanometers.
Okay. Yes, so do shoot some screen capture of those, and then maybe I can talk to you through email.
Okay. Okay.
Yeah, thank you for the lecture. May I ask you one question?
Yes, go ahead, Dr. Lee. We
Yeah,
haven't seen each other for a long time.
yeah,
I'm going to
maybe
I might go to Indiana in 3-4 weeks. I will
oh,
stop by. Probably when the weather is not so bad, then we should have lunch together. Yeah, what's your question?
great.
Yes.
Great, looking forward. Yeah, two questions. Maybe I should keep the first question for next week because you mentioned next week you will talk about the typing mode. I think I will ask my student.
Oh, it doesn't matter. You
listen.
can ask anything. Yes. Yeah.
Yes. Our students have they can image, for example, inorganic and nanoparticle well. However, for biological molecules, for example, like DNA and RNA and nanoparticle, it's quite soft, like a few nanometers, like a triangular, hexagonal shaped. They have difficulty to get the good quality image. So I don't know if you could give us some suggestion how to improve. To make the image better. Typing mode.
Yes. I think the best way is biological molecules mostly works best in liquid. So a lot of these things actually are sample preparation related, and that's the first thing. If I want to talk about biological samples, sample preparation is the emphasis. And then after that, you have to use very soft tip, and the imaging force has to be lower. A lot of bad imagings from biological samples are actually related to the sample imaging itself. Yeah.
I see.
I have a question from the audience, and from Igor Sokolov. Why particular focus on Agilent AFM? It does not seem to be a success AFMs. Yes, Agilent AFM is great when you're imaging in liquid and you do very difficult experiments. And we're all try to pursue something that's very difficult. And I'll be happy to talk about other successful or big cell instruments. How to say that success is how do you do the experiment? And if you could contribute some of your time and give talks, we're happy to accommodate. The Agilent AFM is a very nicely designed tip scan instrument, and some of the performance, some of the experiment is incredibly well suited for Agilent AFM, which you put on a sample scan. Other designs, it's not very suitable, and it's very specialized. For example, if you want to image, image your experiment of a biological sample in salty waters or in sulfuric acid, so on and so forth. That Agilent AFM works extremely well, high-low temperatures. And yes, we will be happy to cover other AFMs, but I'm going to need a lot of more help from the audience.
Yeah, maybe just I can continue my question if you don't mind.
Go ahead.
Like you said, salty water, but what's the problem with pretty much any other research grade AFM?
There's problem number one for sample scan instrument. You have to make sure it does not leak. That have certain things. And then if you want to heat up and cool down your sample at relatively high temperature, a tip scan instrument also has an advantage. And then plus the design of Agilent AFM operation in air and in liquid is exactly the same. So you actually make the liquid imaging much more simple. Yeah.
Okay, be more specific, because technically speaking, like I cannot agree. Because like I tried once to work on this, and I compare with Bruker's micro, well, that time Vico, and pretty much what you listed, it can be done there with no problem, and I think it's a little bit user friendly. So, but I'm really curious because I have no preferences. Maybe I'm missing something, because
you could buy an instrument from us, and I show you how to do the experiment.
Oh yeah, but like before buying, you just need to convince me. Like that's exactly what
I give you a good discount. Anyways, that's a yeah. So yes, there's a particular experiment that was very specialized. Then if you want to heat and cool down your samples, and then the noise level and so on and so forth, there's an advantage of that. And again, we are basically we try to organize the former employees of Agilent Technology and support Agilent users. And then because the company is no longer making this instrument, and then we organize ourselves and maintain their instrument to work for next 10 years. That's our goal. And then we don't exclude Bruker users or Vico users. And then we'll be happy if you help us to expand to that direction. Yes.
Simply like because we are looking for some instrument which would be relatively user-friendly to teach students.
Oh,
which,
okay, yes.
We cannot afford like a new one, but looking at old microscopes. So we try to like think which one would be more kind of students friendly.
Student friendly, yes. The Agilent does have student friendly instruments, and I'd be happy to talk to you off the line. Send me a text.
Okay.
Email. We'll talk about this. Yeah.
Thank you.
Well, also you also have other solutions to propose.
Yes. We probably should talk this off the line and not take other people's time. There's a comment from Jason Marley, and he said, I believe that Gwydion also has YouTube video on basic process. Oh, that's great. That's good news. Yes, I will probably cover my part of it with the Pico image, and I think Pico image is great, but it's a bit expensive. Gwydion is free, so yes. And then if you acquire a new instrument, new computer, I will connect you with the company who makes the software, and then you can buy it from them. It's expensive. Cheap one solutions are Gwydion's. Yeah. Okay, so if we don't have further questions, thank you for your time. Anybody want to stay and ask more questions? You can feel free to stay. I'll be here anyways. Yeah, go ahead. Yeah, what's your question?
So, my name is Quinn. Are we allowed to ask technical, do technical troubleshooting?
Yes.
We talked sort of like last Friday about that noise in the controller.
Yes, I did receive your screen capture of the noise. Could you show me your noise if I give you the host right now?
Not really. The computer that the noise is there on isn't connected to the internet.
Okay, that's fine. Yes, just I'm going to forward the screen capture of noise to the other engineers, and we'll try to get it. We'll try to take a look at this. Yes.
Okay, thank you.
Can you describe a little bit about what the issue is?
The issue is that there's a lot of noise, and it's not really attributed to anything environmental. And it's sort of bled into when I do the frequency suite for tapping mode. So when I do the frequency suite for tapping mode, both the amplitude versus frequency and the phase versus frequency graphs show like extremely jagged edges. Like they look like each of the line is made of like these little plateaus instead of something more straight and smooth. This in result makes the images have like a lot of noise, or like this very stable wave pattern throughout the whole entire image.
Are you okay? Well, let's start with which system are you using?
I'm using the Agilent 5420.
The 5420. Okay, so you're using probably AC mode, not Mac mode.
Yes.
Okay, so the first thing that I want you to check is how secure is your cantilever to your nose. Make sure that it's properly seated. And then also you have an AC block that's inside the nose. It's held by two little screws. Make sure that that's not loose. If that's loose in any way, shape, or form, you're going to get exactly what you're describing.
Okay. I have tried to change out the nose cones, and the problem still persists.
Steve, this is the email she sent to me. That's what this noise is talking about.
Yeah, so that looks like a mechanical interference to me.
Okay.
May not necessarily be your nose. That's just your starting point for troubleshooting. But make sure that the cantilever is properly secured. Make sure that the AAC block is properly secured, because if that block is even a little bit loose, it can cause you a lot of headaches. Aside from that, the next thing that you're going to want to probably do is a deflection stability test with your laser. So you're just going to shine the laser off of the back of the substrate instead of the cantilever into the detector, and then open your time versus signal versus time window and follow your sum signal and your deflection signal over about 15 minutes and see how stable your laser is. If your laser is getting a little weak or a little tired, much like a light bulb, it does have a finite life. It will burn out over time. If your laser is causing some issues, then you're also going to start seeing some problems with your frequency sweep. Because again, like Song described earlier in the presentation, a lot of what your data analysis is being derived from is the laser deflecting off your cantilever. So if we can make sure that those basic things are okay first, then we can dive into the electronics and figure out which module is probably causing your issue.
Okay, thank you. I have one additional point, and I'm not sure how much sense they'll make, but when I have sort of like the photodiode unplugged, and so I'm talking about sort of the laser alignment window where you can see the sum.
Yeah.
When I unplug the photodiode, the rectangle with the sum, it kind of just continually jumps up and down. Like it doesn't remain stable. I'm not sure if it's due to like the noise or if it's due to part of the issue.
That's going to be part of your issue. So it's probably not your laser and it's probably not your mechanical nose. That sounds like you've got something going on with your electronics.
Okay.
Typically what happens is you have a lot of operational amplifiers that are being used, and operational amplifiers are biased with a positive and negative 15-volt power supply. If an operational amplifier isn't properly biased, say you've got positive 15 volts and negative 12 volts, your operational amplifiers start to oscillate, and that creates a lot of noise throughout your entire system. So you could have a bad op amp, you could have a bad capacitor, you could have a bad power supply. But if that's happening, what I would like for you to do for me is take the AC mode out of the loop entirely. So you've got two DB44s plugged into the back of your AC mode. Just unplug those from the AC mode and plug them directly into each other.
Steve, they might not have an AC mode. Last time I
Oh,
tried
if she's using simple AC, that's right, on the
I did a
5420.
Yeah, there's no AC there. Yeah.
Okay, so we can't remove the AC mode, but that sounds like a power supply issue. Song, email me with this content and we'll dig a little bit deeper into it. I'll get you some more information typed up today, but it sounds like you've probably got something going on with your either your head electronics box or your AC or your AFM controller. So I'll walk you through some basic tests and we'll figure out which one's causing the problem and what we need to do to fix it.
Okay, thank you so much, because that means one of our AFMs is down for the time.
Yeah, definitely loop me in. I think my email contact is also in the links for ZoomAFM. You can reach out through Encore SPM services, and I will dig into seeing what's causing this particular issue.
Okay. Is it in the contact us area, or
don't worry about it. If you can find me, I'll find Steve for you. Don't worry about it.
Yeah. Okay.
Yeah, she's already reached out to you, correct?
That's right. Yes, I already received the
email.
Yeah,
just copy me into the email. This is definitely going to be a hardware issue.
Yes. Okay. Okay, so if we don't have any further questions and anyone want to stay and chat, we can stay. Otherwise, well, thank you for your time. And yes, you can log out now.
I was hoping Louis would stay on for a few minutes.
He's maybe busy. I think that's let me remove it. Dr. Lee, I'm gonna remove you because we might have some internal meetings. And also Jason, I'll call you back and when I finish. I remove? Yeah, oh, here it is. Okay, yes, Amanda is my employee, so it's fine.
Once again, very well done, Song. Nice job. I like how you got a little bit more detailed on some of the content and you shortened it a little bit so that it wasn't an hour-long presentation. I like that you give a little bit of information about how the system is working, and then you open up the floor for Q&A, which is fantastic. Amanda, you did an awesome job monitoring the chat and helping people stay focused. One thing that I think we should probably add a little bit to towards the end is a little bit of advertising, right? Louis, you and I had talked about how do we probably monetize this a little bit. If you think of it more like a commercial than a presentation, at the end, they sit through a quick presentation of upcoming products like the Galaxy controller. That could be a marketing tool for you, and you can have SignTech pay you to advertise that at the end of your presentation.
Yeah, we could
Does
do
that make sense?
Yes, but now today we have 2 people express interest to buy a easy to use instrument that's low cost too.
Yeah.
In the chat,
Yeah.
right? So I'm a little hesitate to immediately bring up SignTech because that might exclude all the people who's pro Vico. You know, those people are very proud.
Don't get me wrong. Don't get me wrong. I'm saying that this is a potential opportunity for you to generate revenue, right?
Yeah.
Because again, you're doing this completely free on your own time, right? You're not getting much more than a lead out of this than anything else. So if you can have a company like SignTech pay you each week to advertise their product at the end of your presentation, that will help you continue to fund this project for you. It doesn't have to be just SignTech. You can advertise micromesh, right? Different cantilevers, different samples. You could advertise maybe some of your samples for NanoQ, right?
Yes. Yeah.
But if you put a little bit of an advertisement theme to the end of the presentation, people can drop off. They don't have to listen to it.
Yeah.
And then you've
At
got
the
other
end,
companies paying you to talk to customers and generate leads.
Yeah,
That's a great idea.
I tried to talk to Nicholas, and then he's very busy in biophysics. So I should probably talk to him this week, and then he will advertise the nano and more guys, right? Those, and then his hesitation is that if we work with 1 or 2 AFM companies and they view as competitor, that's his hesitation. So I did not push. I deleted that slides with SignTech and so on and so forth. I'm thinking let's make it big first, right? Let's make it big, and then we know everybody anyways. And if you put SignTech, that it make ego kind of like he basically says you are not good. Vico is good. I did not want to hit him because we're not aggravating, right?
That wasn't the best forum for a debate on who has the best AFM. That's not the purpose of this at all. So I agree with you.
If you want to present, if you help us to cover the Vico, great. I will welcome you because we wanted to advocate to all the older AFMs.
Yeah.
And even we reach out for people who is repair the Vico AFMs. Think a little big and not to immediately make, because if we know who they are, we can sell things to them, and not in front of people anyway.
Yeah, this was definitely not the forum for a debate on who's got the best product. That's not what we're here for.
No, we welcome.
But to throw in a little bit of advertising for you to generate some revenue, I think would be a good idea. It would be an appropriate ending to your presentations. Because again, they don't have to sit there and listen to the commercial ending of what you're advertising. But if people are interested, it can generate you some more leads. And you've got the companies that are actually selling these products paying you to advertise it.
Well, that's definitely is the long time goal. Yes.
Right.
Okay.
Okay. Aside from that, I don't remember what that other lady's name was because it was a complicated name. and I'm an English guy, so I don't understand things other than Kelly and Steve, right? So if you could, please contact me with her email and I will get back to her.
I have them written down. I have all the questions written down.
Awesome. Yeah, I just need her contact info so that I can reach back out and find out what she needs.
I'll forward that email. Amanda is working on get people to RSVP and provide their phone number and so on and so forth on the background.
Oh, that'd be good. Yeah, contact info is going to be important. So
I'm sorry. I direct messaged the First Lady, Nia Gupta, and got her email. She had the questions about the data analysis, learning more. So I got her email directly. And but I don't have Quinn's email. Song has that. So Song, you have to send that to him.
Yeah, you can just forward it over to me and I'll reach out to her as soon as possible.
Yeah. Okay, good.
And I'm glad to see that Louis joined in too, but